Okay, so this is the last section, chapter 5, for us to cover. It's called diagonalization. And this is going to show us one reason why we would bother with doing eigenvalues and eigenvectors. It's certainly not the only reason, and it's maybe not really not even the most important reason, but it's one that we can see for now. We will see another reason for it a little bit later after exam 2. Anyways, okay, so let's suppose we go back to the first example we had, 1, 2, 2, 1, and I asked you to find a squared. Well, what does a squared mean? It means a times a, so we would have to do 1, 2, 2, 1 times 1, 2, 2, 1. Okay, so let's see here. It's going to be 1 plus 4 is 5. 2 plus 2 is 4. 4, 5. And we get our answer. And what if I asked you instead to find a cubed? Well, that's a times a times a. And you could, work this out. We already know what two of them multiplied gives you 5, 4, 4, 5. And if we finish that, then, let's see, 5 plus 8 is 13. 14, 14, 13. So that wasn't too bad, but what if I asked you to say, find a to the 10th power? That sounds a lot more annoying, right? We have to write it out 10 times, do all this multiplication. What if instead I asked you to find a to the 100th power? Or if you don't like that, how about 1000th power? And so when you try to do matrix powers with high numbers, it gets really, really insane really, really fast. But it turns out we can use eigenvalues and eigenvectors to get the answer really, really quickly. So let me show you how this is going to work. So we start with the same matrix, 1, 2, 2, 1. And then what we're going to do is we're going to find the eigenvalues and eigenvectors. Well, we already did that before. The two eigenvalues are 3 and negative 1. And the corresponding eigenvector would be 1, 1, and 1, negative 1, right? We saw that in the very first video and then the second video. And now I kind of want to show you something here. So if I do a times 1, 1, I get 3 times 1, 1. And if I do a times 1, negative 1, I get negative 1 times 1, negative 1. And so if I combine these together, then if I do a times the matrix 1, 1, 1, negative 1, I would get 3, 3, negative 1, 1, which is the same as 3, 0, 0, negative 1 times 1, 1, 1, negative 1. Let's just double check this here. Oh, sorry, I messed up. Okay, so how do we write this? It's going to be... Yeah, sorry, I put them in the wrong order here. It's going to be 1, 1, 1, negative 1 times 3, 0, 0, negative 1. Okay, so double check that that actually is correct, and it should be. So basically what I see is if I take a times the matrix 1, 1, 1, negative 1, it equals to the matrix 1, 1, 1, negative 1 times 3, 0, 0, negative 1. And if I call this matrix P here, this is the same P over here, and what I can do is I can multiply by P inverse to cancel this part out. And what I would then have is I would have A is equal to 1, 1, 1, negative 1, 3, 0, 0, negative 1, and then whatever the inverse of this matrix is, or shorthand notation, P, D, P inverse. And specifically I want to point out that this D here, this is a diagonal matrix. So I haven't really done much work yet because we already knew what the eigenvalues and eigenvectors were. But I just show you that you can write A in this format, PD P inverse. Now, since I have it this way, what happens if I square it? Well, again, it's A times A. Each one of them is PD P inverse, PD P inverse. And if you look at this inner part here, P and P inverse cancel, and I would have PD D P inverse, or PD squared P inverse. And it turns out you can repeat the same thing. If you want to do, let's say, A to 100, it's going to be PD to the 100 P inverse. And if I want A to the 1000, it's going to be PD to the 1000 P inverse. So by doing it this way, if I want to find the power of A, all I need to find the power of is this D matrix. However, it turns out that if you ever have a diagonal matrix, and again, this only works for diagonal matrices, and you raise it to any power, all you have to do is raise each of the diagonal elements to the same power, and it will work. So let's do the actual example here now. Let's find, for the matrix A, let's find A to the 5th. So from before, my P was 1, 1, 1, negative 1. And in case you didn't notice this, this is just going to be the two eigenvectors joined into a matrix. And my D, that's the middle one, that's going to be 3, 0, 0, negative 1. And the last thing we need is P inverse, which you can put it in your calculator, or you can do your 2x2 trick here. Let's see here. That would be determinant of -2, so you divide by that. So it's going to become 1/2, -1/2, 1/2, 1/2. That should be your inverse matrix here. And so what I then do, if I can take A to the 5th would be, again, P D to the 5th, P inverse. That's 1, 1, 1, negative 1. D is 3, 0, 0, negative 1 to the 5th power times 1/2, 1/2, 1/2, negative 1/2. And again, we can work out the diagonal to the power pretty easily. 3 to the 5th power. Let's see what that is. 3 to the 5th power is 243. -1 to the 5th power is -1. And then we multiply these here. I'm going to have 243, -1, 243, 1. And then my final answer here is going to be 121, 122, 122, 121. And this is A to the 5th. And that really didn't take that much work. And we could have done A to the 100th pretty much just as easily, or A to the 1000th. The only problem is you would need to worry about what, 3 to the 100 is. That's kind of a big number. 3 to 1000 is even bigger. But regardless, you can do this process here for anyone. Once you have your eigenvalues and eigenvectors, you just put in this little kind of formula here and you calculate it. So what you can expect on your exam is I will give you a 2x2 matrix like this. Part A is find the eigenvalues and eigenvectors. And then part B is going to be raise it to the 5th power or the 10th power or something like that. And so you're just going to use this method here to do that. Okay, so you can expect a problem just like this on your next test.